Questions at all in this class and stuff? You guys see the new homework? Okay. Yeah, we're back to the normal homework schedule. Homework's due on Wednesdays. The last homework I'll mention, that's a couple weeks from now, is going to be due like after the last class to try and cover as much as we can before the final. Okay. Yeah, any questions at all? Otherwise, I'll go ahead and get going.
Sorry. Is there a table of Fourier transforms like on the Canvas page, or is it just something that we have to just like look up ourselves?
My bad. I'll upload one. I'll upload it. Sorry about that.
Thank you.
If I don't do it after this, like within the next, let's say, hour after class, send me an email to remind me, please. Okay. All right. So this was a while ago because we didn't have class on Friday, and so let me sort of remind you guys what we were actually doing. Okay. We were talking about this idea called perturbation analysis, right? And it's an approximation technique that allows us to solve complicated differential equations, basically. And so we were trying to make things simple by dealing with mass transfer, so we don't have to deal with tensors and stuff, right? And so we're talking about this reaction diffusion equation right here. We're able to non-dimensionalize it, got to an equation that looks like this, where epsilon is defined here, and then these are the non-dimensional variables, the non-dimensional concentration and some non-dimensional length. Okay. In this particular case, we were actually able to just solve this equation directly. This equation is not that difficult to solve. But, excuse me, pretending like we wouldn't be able to do that, we started looking at what would happen if we had to approximate. And so, for instance, one of the things that, one of the limits where an approximation will work really well is when epsilon is much, much less than 1. Okay? When epsilon is much, much less than 1, then the procedure is to assume that your final solution here can be written as a Taylor expansion. In terms of epsilon, so you expand in terms of powers of epsilon, where each of these terms in the Taylor expansion, unlike a normal Taylor expansion, here these would all just be functions rather than constants of C, our position variable, right? And then when we plug this in, then we can match the powers of epsilon here, and then look for equations for each of these. Different powers of epsilon. We do the same thing with the boundary conditions as well. This is how we got the different boundary conditions. And so we get a series of differential equations that goes all the way out to infinity. You can do as many of these as you want to your little heart's delight. And then figure out what the solution to these differential equations are using the boundary conditions that we also get using a similar procedure. And then, of course, the more of these you do, then the better approximation you do. But as we showed you, when epsilon is small, you really only need a few leading terms, and then you can actually get pretty close to what the final solution was. And this is sort of where we were at. You know, it's basically just solving the individual solutions. The first one was really easy. The second one, you actually use the solution from the first one. You'll see that a lot in these regular perturbation expansion problems, because of the way that the original differential equation is formulated right here. Then it makes it such that in each of these equations, the next term kind of depends on solution to the previous term and stuff, right? Again, you have to plug in the boundary conditions and everything, and then you can basically get additional leading order terms, et cetera, et cetera, et cetera, and then basically keep going as long as you really want. Okay. And then I believe at the very end of class on Wednesday, what I ended up doing was plotting our solution for this problem, which we know already. That's given by this because our problem happens to be something that we can actually solve pretty easily analytically. And then showed you guys that our perturbation expansion actually works out really well at limits of low epsilon. Okay. I'm going to go through two things today. First, I'm going to show you a case where we don't have the solution to the an analytical solution. Okay. And then the second thing that I'm going to show you is what happens in the other limit when epsilon is much, much, much greater than 1. Okay, you can imagine that is going to be a different type of perturbation analysis here, because you can't really do a Taylor expansion when the variable that you're Taylor expanding over is really large. Okay, so let's go ahead and do the first thing here. So I'll just say, what if my pen is a different size now? Let me see if I can fix that. That's better. Okay. Come on. Okay, now my pen doesn't work. Give me a second while I go get a new battery for my pen, sorry. How are things going, guys? Okay, I believe we are back in business. Okay, so the question becomes, what if the ODE is different? Okay, so the ODE that we were dealing with before looked like this. This is, of course, suitably non-dimensionalized. And then we also had boundary conditions that said that the concentration is equal to some constant at the edges of our catalyst slab. Okay, and so this was a first order consumption, the first order consumption of some sort of reactant in our system, right? And so we were able to solve this problem because this is a linear ordinary differential equation, right? And then this is what gave us the hyperbolic cosines and sines and everything, right? Now, if our equation looked instead like that, that's a second order differential. That's a second order rate constant at this point, right? Or second order rate law. And this is not something that we can solve very easily at all using standard differential equation techniques, right? I don't actually know what the solution, what the general solution to this differential equation would be, and I'm not going to attempt to solve it. Instead, if we still have our case where epsilon is much, much less than 1, then we can do regular perturbation. So again, sorry, just to jog your memory, we'll use this general solution based on sort of like a Taylor expansion. Like that, right? And we'll just go ahead and plug that in. And just like before, we plug it in and we match different value, we match different powers of epsilon, right? And so this first term right here is just the derivative of this equation, or the second derivative, sorry. Okay. And then the second term right here is again just the original equation here. Not epsilon 1, sorry, epsilon. And then we need to match powers of epsilon. To do that, actually, notice how this has epsilons in it and stuff, and so we actually need to multiply this guy out here, right? So this is actually, I'm just going to do a few of the initial terms. Okay, this f0 squared, obviously there should be an f0 squared. That's what happens if you were to multiply this term by itself, right? This term right here comes about if I multiply this term by this term and then this term by this term, right? When I multiply these two expansions out, and that's why there's a 2 right here, right? For the epsilon squared term, for instance, it might be a little bit more complicated. You would get it when you multiply this times this, and then of course this times this, right? And then you would also get it if you were to multiply this term by itself. So you would get something like epsilon squared, f1 squared plus 2 epsilon squared, f0, f2, etc. Like that, right? And just like before, we need to match orders or match powers of epsilon, right? And so if we were to do that, then we could look at the equations that have, or the terms that have 0 order epsilon. That would just be this term right here, right? So we would get something like this, right? Then we also have the first order epsilon, so order of epsilon 1 terms. That would give us an equation that looks like this. Right? Because this is an epsilon to the first term. This is an epsilon to the first term, right? We would also have an epsilon squared term. Okay. Notice how this looks a little different now than before, right? And also, just like before, we need to deal with the boundary conditions, right? The boundary conditions say that at c equals plus or minus 1, then f equals 1, right? And of course, f is equal to this expansion right here, so let me just plug that in. And just like before, we also have to match orders of epsilon, right? So if we match the 0 order of epsilon ones, then that's f0 has to equal 1. Make these dots a little better, sorry. f0 equals 1. We also get that f1 equals 0 because on this side, the epsilon first term is f1. On this side, the epsilon first term is 0. There's no epsilon to the first term. And same logic for f2, and etc. Okay? And so just like before, we can solve an infinite number of ordinary differential equations, basically as far as you really want to go, and then you can get your solution. Okay? For instance, we can look at our order of epsilon to the 0 term. Okay? We have to solve this differential equation with these boundary conditions. Okay, let me just rewrite those for completeness. Okay, and like before, that implies that our first term is that. Okay. We could also solve this next term right here. This gives us okay, like that. That's our ordinary differential equation, but we know what f0 is, and so we can go ahead and just plug that one right in. That's just 1. Okay. And of course, we also have boundary conditions. F sub 1 at plus or minus 1 is, in this case, going to be equal to 0 from right here, right? And then, of course, you can also solve this differential equation. We actually solved essentially this differential equation earlier, and so I'll just go ahead and write down the solution. You get something like this. And then you can do the same thing, order of epsilon squared. I'm not going to do it, but basically you solve this differential equation with these boundary conditions, and you plug in. So for instance, this differential equation right here. Right? You would plug in what we know from these already. F0 here is 1, and F1 is this guy right here. And so this looks like this. Right? With boundary conditions that we wrote earlier. Right? And of course, you guys could solve this differential equation, probably without too much difficulty, right? You just integrate twice and then plug in the boundary conditions. And so I'm gonna spare you guys the details of that. Okay. But this is in general how regular perturbation expansion works. The overall procedure is you assume that your solution is going to be a Taylor expansion around the variable that is going to be small. You plug it in, and then you match different orders. You end up with a family of ordinary differential equations, and then you get what the solutions are for each of those ordinary differential equations. Of course, paying attention to the boundary conditions as well, doing the same thing for them, expanding it out, and then finding boundary conditions for each of those different orders. Okay. So, as I mentioned earlier today, what I'm also going to look at is what happens we're dealing with the other limit if epsilon is much, much greater than 1. Okay. Just to remind you, this was our original problem. So let me go ahead and work with the original problem here. Okay. That was this with boundary conditions that, right? The definitions for our various terms here, just to remind you, were F is the non-dimensional concentration. Okay. Our C is our non-dimensional length. Okay. And then our epsilon was some sort of grouping of the different experimental parameters that we have, kh squared over d. Okay. And so if epsilon is much, much greater than 1, okay, then, you know, maybe we can do something similar here, right, as what we were doing before, except, you know, it's kind of annoying to have this term go to infinity, and so maybe instead we can try and do a perturbation expansion where we look at, let's say, a delta that's defined as 1 over epsilon, right? Okay, so if delta is equal to that, sorry, if epsilon is much, much greater than 1, that implies then that delta is much, much less than 1, right? Makes a lot of sense. So maybe we can try the perturbation again. Okay. So here's what our differential equation looks like now. Okay. I could multiply through this equation by delta, and I'll get this. Okay. And the boundary condition is still the same, stay the same. Okay. Now let's, for instance, look at our order of deltas to the 0 solution, right? That solution is what we get when we just let delta equal 0, right? It's kind of like up here when we looked at our order of epsilon to the 0 solution right here, then our differential equation just became this, right? Because it's as if we let epsilon go to 0, right? Our differential equation was this, and then we were able to solve it very, very easily. Okay. Let's see what happens when we let delta go to 0. Okay. Then what happens to our ODE here? Well, what do you guys think happens to this ODE? It's pretty simple, right? This term goes to 0. So what we get then becomes F equals 0. That's the ODE. That's not an ODE, right? That's just a solution. The function, the solution is just that F is equal to 0, right? I'll say the ODE is gone. Okay. That doesn't mean we're done though, right? I mean, in theory, we solved the ODE because we didn't even have an ODE, right? But it's really weird here because we have boundary conditions right here. The boundary conditions say that f has to equal 1 at c goes from at c being plus or minus 1, right? Physically, remember, this is that the concentration is equal to some constant at the sides of our catalyst slab reaction of our porous medium here or something, right? And yet somehow what we found is that the concentration of the catalyst is 0 everywhere, right? And so we violated the boundary conditions, right? So I'll just say what happened. Okay. All right. To look a little bit about to look a little bit at what actually happened here. Let me play around because we're a little lucky here, right? We know what our solution is going to be, right? If you recall, so I'm just going to go into my old commands here. If you recall, you know, this was what the actual solution looked like. Assuming it'll give me a figure soon. You guys can see my MATLAB that I opened up, right? Okay, cool. Okay, not sure why it always takes so long to give me a figure, but okay, sure, there's a figure right there, right? And this was our solution once we had 2 orders of the regular perturbation expansion, right? Now, of course, we could also do the same thing, but having our epsilon be really large, let's say 100. Okay. If that's the case, let me go ahead and plot my solution here. My solution looks like that. Okay. Now, I'm not going to go ahead and plot the regular perturbation expansion. I did this a little bit on Wednesday. You guys hopefully remember that the regular perturbation is terrible. The regular perturbation expansion is terrible in this limit when epsilon is really large. That's not a surprise. The Taylor expansion only works when you're in the neighborhood of a point, right? But let's look at a little bit what happens physically in this case. Remember the solution from our notes behind. There's the notes, right? The solution was that f is equal to 0. And it turns out that, well, f is actually equal to 0 for the most part, right? Let me convince you this even more. Let's say instead that epsilon is equal to 1,000, okay? I'll go ahead and plot it again. It turns out that for the most part, f is actually equal to 0, right? Physically, do you guys know what's happening here? Like, why would f be equal to 0?
The rate of reaction is occurring much, much faster than any sort of rate of diffusive mass transfer.
Exactly. Reaction is much, much faster than diffusion, right? And so you're consuming all the reactant. And so it totally makes sense that the reaction should be equal to, or that the concentration of the reactant should be equal to 0 throughout our material here, right? But we still have this pesky issue with the boundary conditions. The boundary conditions say that the concentration has to be equal to some C0 outside of the material or at the edges of the material. And you can see that for the most part, our solution here is correct, except over here when we start going into the boundaries. Okay. And so what I'm going to talk about for the rest of this class is basically how to deal with this little thing at the boundaries here. And it's a technique also called perturbation analysis, but instead it's called singular perturbation. You kind of have a clue when you're dealing with singular perturbation. When you stare at your original ODE over here, and if you let your parameter go to 0, then you actually start dropping derivatives, or you start dropping the leading order of the derivatives here. In this case, when we drop the leading order derivative here, the second order derivative here, then you actually just get nothing, right? You get no ODE anymore. And that's what led to this crazy thing. Remember, as we kept saying, we've said this so many times in this class, right? For every derivative, you need to have a boundary condition, right? And you can't have too many boundary conditions for the number of derivatives that you have, right? In this case, our perturbation analysis, or our approximation, basically took our ODE, second order ODE with 2 boundary conditions, and turned it into a 0 order ODE, still with 2 boundary conditions. So that's why we can't really solve the problem. Does that kind of make sense? So singular perturbation is something that we use when we start seeing these scenarios, okay? And the key with singular perturbation is that we were dealing with the wrong length scale here, okay? If you remember how our problem here was formulated, our problem here said, okay, we're going to non-dimensionalize our F, or our non-dimensionalize our concentration by some C0. That's probably still fine here, right? But we're going to non-dimensionalize our position by H. That's the thickness of the slab of material, right? What that implies is basically that most of the change over, most of the length at which the concentration changes is going to be across the length scale of the entire material here. Okay. But as you saw from our solution right here, that's not actually true. Perhaps the length scale that we care about is actually somewhere in here, right? So what I'll say is, there we go. Okay, computer's a little slow, sorry. So singular perturbation, it's useful when we lose the leading order derivative when applying approximation. Okay. And the reason we started losing our leading order derivative is because we had the wrong length scale. Okay. And that's because before we used this definition. C is equal to X over H. Okay. But that's not really the right length scale here, because all of the action doesn't happen over a length of H. It actually happens over a much thinner layer near that boundary, right? So instead, there is another length scale. I can't spell, wow, or I can't write another length scale here. Okay. If we wanted to look at the lengths, or if we wanted to surmise what a length scale might be over here, perhaps I can play with the parameters of my problem and actually come up with a better length. This length right here is when reaction and diffusion kind of balance each other, right? What happens in here, okay? You can imagine then that right there could be a good length scale. Okay. The way I know this is because, well, diffusion has units of meters squared per second, length squared per time. And Lindsay will probably kill you guys if you don't know what the units of the rate constant is, right? Anyone know what the units of the rate constant is? It's inverse time, right? Right. And so length squared over time divided by inverse time gives me a length squared. Square root of that gives me a length, right? So it's just, I was just playing with the parameters a little bit. When you deal with other singular perturbation problems, there will be a length scale that naturally falls out. We're going to do this in a second if we have time later today. If not, then on Wednesday for the full Navier-Stokes equations, and then it'll also be clear what that length scale actually comes about. But that'll come a little bit later on in the class. Okay, but I'll say this has units of length. Okay, and so what that means then is we actually have to split our problem into two. Okay, before, well, here, I'll just say this. So we have some f of x as a function of x, right? We're interested in the concentration profile from x equals 0 all the way to some h. Excuse me. And as we saw from our plot earlier, our solution looks something like this, where this right here is 0. Okay? And what we have here is somewhere in this length right here, which could have a length of d over k. Okay? Kind of works out too, when k gets really large, then this length gets really small, right? We have what we might call a boundary layer problem. Okay? That's basically where all the change in concentration comes in. And then, of course, out here beyond that, we have a bulk problem far away from the boundary. Okay? And so perhaps it makes sense then to actually redo our axis, to redo our axes here. Instead of calling my position variable an x that goes from 0 to h, I'm going to redefine my axes this way, a y. My y is going to go from 0 to this direction. Okay? And my y is going to be defined in terms of our new length scale here. Okay? It's going to be a non-dimensional variable, just like before, except it's going to be defined in terms of our new length scale. Okay? So I'll say in the boundary layer, man. I'll define a new position variable. Okay, that position is going to look like this. You guys see what I did there? When x is equal to h, y is equal to 0. And I'm non-dimensionalizing this h minus x here versus using my length scale here. In terms of the variables that I've already introduced earlier, this is fairly easy. So for instance, I could write this. Right, because c is just x over h, right? So that works out. And then it turns out that this guy right here, down here, this is a square root of d over k. If I were to pull this h into the radical here, then I would get square root of d over kh squared. Kh squared over d is just epsilon. So 1 over epsilon. So delta is just d over kh squared. So this is actually just, if I can write, this is actually just 1 minus c over square root of delta. Okay. So this is this is basically just, re-expressing my position variable. Okay. It's still a non-dimensional position, except now I'm dividing through by a square root of delta here, as that is my length scale here. Okay. Let's look at our PDE now. Okay. I'll say original PDE was this. Okay. We can now, instead of expressing stuff in terms of c here, we can now express it in terms of y. To do that, we need to kind of re-non-dimensionalize. Let's just go through all the chain rule math and stuff like that. Okay. The new PDE, well, we need to figure out what df dc is, right? So to do that, we'll apply the chain rule. df dx is df dy times dy dx. Okay. Now dy dx you could actually calculate pretty easily from this, right? That's just minus 1 over square root of delta times df dy. And by the same logic, then d squared f dx squared is equal to 1 over delta times d squared f dy squared. Okay? And so if I were to take this guy and plug this into here, then my new PDE becomes this. Okay. This is a pretty good hint that we're on the right track. We picked the right way of rescaling our y value here. The reason is because, whereas before when delta goes to 0, this term goes away because, you know, when delta goes 0, then this term gets really small. Here, when delta goes to 0, nothing happens. The diffusion term here balances this reaction term. And that's how we know that we picked the right length scale, d over k, square root of d over k. Had we picked something different, then we would not have had this nice sort of neat way. It turns out that in this particular problem, there aren't enough parameters that you really couldn't have picked any other length scale here, right? But this is one way that we know that, hey, we actually are sort of on the right track here. Okay, so I'll just write ODE balances reaction and diffusion terms. And that's because we're in the boundary layer. Okay? And so here's a differential equation that we can solve. We're going to need boundary conditions for that differential equation, right? So what are these boundary conditions? Well, this was our original problem here, right? We had that our concentration is equal to some C0, so F is equal to 1 at x is equal to h. When x is equal to h, then y is equal to 0, right? And so what that means is, I'll call this BC1. At y is equal to 0, which again is what happens when x is equal to h, then we have f is equal to 1. Okay? There's one more wrinkle in our analysis, though. We need another boundary condition. Again, for every derivative in our problem, we need a boundary condition, right? In our original problem here, we had a boundary condition. Whoops, sorry. Here's our original problem. We had a boundary condition that f is equal to 1 at c is equal to 1, so when x is equal to h, right? And then we had the other boundary condition, f is equal to 1 when c is equal to -1, right? We could use that as the other boundary condition, right? But that would kind of destroy the whole purpose of this whole exercise here, right? What we're really talking about is breaking up our problem into a bulk problem, which it turns out we already solved, as I showed you guys over on the MATLAB segment here. It's actually already done. We had the correct solution, right? When we're over on this side of the close to the boundary, we don't actually even know or care about what happens all the way over here, right? And so instead of perhaps trying to use that second boundary condition at c equals -1 or when at x equals -h, instead it might make more sense then to match what we already know from the bulk solution problem. And the way we're going to do that is then we'll say that at y equals infinity, so far away from the boundary, f is equal to 0, right? And this is, again, to match the solution far from the boundary. Okay? All right, now we can actually solve this. Does anyone know what the solutions to this equation are?
Is it exponentials?
It's just exponentials, right? As a quick aside, we could have also used hyperbolics here, but in general, we don't use hyperbolics in situations like this. When we're dealing with infinite domains here, when our y, in this case, goes from 0 to infinity, it makes a lot more sense to use exponentials. Here's why. I'll show you immediately. You'll see it in just a second. Okay, so the solution is f of y is equal to c1 times e to the y minus c2 e to the negative y. Okay, if we apply our boundary conditions, then we know that c1 has to be equal to 0, right? Because the solution has to approach 0 when y goes to infinity. So this is the only term that can be there, right? And if we apply our first boundary condition, f is equal to 1 at y is equal to 0, well, you plug in a 0 here and a 1 here, and you know that c2 has to equal negative 1. Or sorry, this should be a plus. I don't know why I put a minus there. c2 has to equal 1. Okay, so we just apply the boundary conditions in our head. It's super simple. Okay, so after we apply the boundary conditions, we get that f of y is equal to e to the minus y. Okay, that was super simple, right? Now, of course, we're in this sort of weird, funky world here where we only care about what happens near the boundary. So we need to translate it back to what we already know here, right? So let me go ahead and do that. The y is just defined as 1 minus c over square root of delta. Or maybe in terms of things that we can plot more easily, we were plotting everything in terms of epsilon earlier, right? Epsilon is just 1 over delta. So that's the solution. Okay. And so this is something that we can actually plot. So let's go to MATLAB again. And remember, this was our solution here, right? So now I'm going to plot that. That's our solution, right? And hopefully this will work out. You see what happened to my plot? Now this is the red line here. This is what I just plotted. It falls exactly on top of the previous line, right? You guys want to see that again? For those of you that weren't paying attention. Okay, so my original solution, let me just go ahead and delete right here. My original solution was this. This is what I showed at the beginning of class, right? My new solution is right here. And you know what? I'll make it a little bit larger too, so that we can see it a little better. My new solution is this. Okay, this is what happens at the boundary layer. If I plot that, that's what I get. Okay, and so our solution is totally right. Now, our solution is not correct way over here, but we don't care about that, right? We only are caring about what would happen in this boundary right here. If we wanted to care about what would happen in this boundary, then we would redefine our axes the other way, right? And then, you know, redefine it such that the y is going to be closer to x equals minus h rather than plus h. Okay, does that all kind of make sense? All right, so in general, that's how singular perturbation works. It works because our overall solution actually works for the most part, but all the action happens at the boundary. And so we need to rescale our equation here according to what happens at the boundary. All right, I only have 15 minutes, even less time than that, and I'm gonna go ahead and stop here because the next piece right here is gonna take a little bit longer to deal with. And so any questions at all right here? Otherwise, I'm just going to go ahead and end class. Okay, cool. All right, thanks. Thank you guys so much. I'll see you guys on Wednesday.